Okay, there's a technique that's used quite a bit in 4.3 as well as elsewhere, where we're interested in the behavior of not only the first derivatives as well as the second derivatives, and it is something that you have seen before. So say for instance, the first derivative of some function is this. One of the things that we already know that we're interested in is where the derivative is equal to 0. But we're also going to be interested in where the derivative is positive and where the derivative is negative. And the way that we found that is a sign chart. And when we've done sign charts before, we have set our items equal to 0. And then what we've done is on a number line, put in these values. And again, you can spread them apart so you nicely create regions here. So our 2 cuts in the number line creates 3 different regions. Our region 1 here is going from negative infinity to -2. Region 2 is going from -2 to 4. And region 3 is going from 4 all the way off to positive infinity. And notice those are all open intervals. We're not including the endpoints here. So what we will then do is bring these down to keep these regions separate from each other. And then we're going to list out each of our factors individually. And I like to list them out in the order that they create points on the number line. So I'm going to put x plus 2 first. I'm going to put x minus 4 second. And what you will see in the book is the way that they go ahead and get values for a sign chart is they'll pick test points. So, and usually when you pick test points, pick numbers that are easy to deal with. So -3 is in region 1, 0 is in region 2, 5 is in region 3. Now note I picked the very first integer to the left of -2. I picked the very first integer to the right of 4. And I picked 0 because 0 is always easy to evaluate. And what they would do with these test points is they would go ahead, plug them into the factor there to go ahead and see what we get. Mostly being interested in positive or negative. Now, if we wanted to graph this, it's always nice to have additional points, and that's what we would take the number parts for. But what we're really more interested in here is the fact that in the first region, x plus 2 is negative. In the second region, x plus 2 is positive. In the third region, x plus 2 is positive. When you have linear factors, you may also think of it as, if you thought of that line. So here is the line x plus 2. There's -2 there. And before -2, it takes on negative values, and after -2, it takes on positive values. It's a linear factor with a positive slope, so it's going to be negative till it becomes positive, and then it stays positive. And let's go ahead and use that approach on x minus 4, we know that x minus 4 until it hits 4 is going to be negative, and then it's going to be positive. After we have that, we can go ahead and put these back together. So x plus 2 times x minus 4, this is going to be a negative times a negative. That's going to give us a positive value there. This is going to be a positive times a negative. That's going to be negative. This is going to be positive times a positive. That's going to be positive. So we know that our derivative is positive or greater than 0 on negative infinity to negative 2 open interval, as well as from 4 off to positive infinity. We know that our derivative is 0 on the interval from negative 2 to 4, the open interval. So on these intervals, our function is increasing. On this interval, our function is decreasing. When we do this for a second derivative, it's going to give us insight on the concavity of the function. So, and this is actually why a lot of our derivatives earlier, we saw the answers written in factored form. We have that derivative simplified into factored form. It's pretty easy for us to go ahead and find the zeros of it so we can get this process going.